Hey everyone, we are going to talk about topic 2, which topic 2 is a pretty large topic in IB physics. It's where a lot of the stuff that people think of as physics happens. So we're going to be on topic 2 for a while. 2.1 is the very beginning of studying motion. So we won't do forces in topic 2.1. 2.1 is really more about what's called kinematics. Let me add a page here, write that down. So, mechanics. What we're studying, this part of physics is called mechanics, and mechanics is the study of motion and the causes of motion. And you can break mechanics up into kinematics and dynamics. Kinematics is really the study and description of motion, and dynamics is really the causes of motion, which are pretty much just forces. To fully describe something, you need to be able to explain its motion and track it and predict where it's going to be, and you also need to be able to analyze the forces on it which are causing that motion. So the first thing we're going to do in 2.1 is really mostly kinematics and describe motion and come up with some equations that can predict what something might do if it has a certain acceleration and a velocity, that kind of thing. Dynamics is where, let me get that, go away. There we go. Dynamics is really where all of Newton's laws fall, which deal with forces and the causes of motion. Okay, so topic 2.1. There's some basic definitions that happen in topic 2.1, like speed and velocity and displacement and distance. But I like to start with a description of motion, so the question I pose in class is, how do you know if something is moving? And that seems like a really simple question, and most people say that you just look at it and you can tell it's moving, but you got to dig deeper and really, how do you know when you're looking at something if it's moving or not? What is it that you notice that lets you know that a thing is moving? And usually in class we'll have some back and forth, and eventually someone will say something about its position, or someone will say something about you see things in the background and it's not in the same spot if you look at an object. So eventually we stumble upon the idea that you have to compare where something is to something else. And by doing that, you can know for sure if something has moved. And so that's called using a frame of reference to measure something's position relative to. So there's a great video I always show that if you watch, it's a long video. We only need the first few minutes for what I'm talking about right now. But in the 60s, there was a series of scientific scientific educational films made, and they put in a lot of thought to them, and this is one of them. And yeah, it's from the 60s, so it's black and white, and the guys sound like they're from the 60s, but it is pretty trippy.
We are used to seeing things from a particular point of view, that is, from a particular frame of reference. And things look different to us under different circumstances. At the moment, things look
You look peculiar. You're upside down.
No, you're the one that's upside down.
No, you're upside down.
No, I'm not. He's the one that's upside down, isn't he?
Well, let's toss for it.
All right.
Okay. You lose. He's the one that's really upside down. You better come into my frame of reference now.
My frame of reference was inverted from what it usually is. That view of things would be normal for me if I normally walked on my hands.
This represents a frame of reference. Just 3 rods stuck together so that each is at right angles to the other 2. Now I'm going to move in this direction. You see the frame at the same spot on your screen, but you know I'm moving this way because you see the wall moving this way behind me. But how do you know that I'm not standing still and the wall moving? Now the wall has disappeared and you have no way of telling whether I am moving or not. But now you know that I'm moving. The point of this is that all motion is relative. In both cases, I was moving relative to the wall, and the wall was moving relative to me.
All motion is relative, but we tend to think of one thing as being fixed and the other thing as being moving. We usually think of the earth as fixed, and walls are usually fixed to the earth, so perhaps you were surprised the first time when it was the wall that was moving and not Dr. Hume. A frame of reference fixed to the earth is the most common frame of reference in which to observe the motion of other things.
So from that video, you should be able to tell at least that there is such a thing as frame of reference, and you can think of different things as your frame of reference. So humans are used to using the earth as our frame of reference because it makes sense. Because from our perspective, looking around at the earth, everything is motionless. You know, trees attached to the ground, they're not moving with respect to everything else that's attached to the earth. But if your goal is to shoot a rocket into space and land on the moon, you probably don't want to use the earth as your frame of reference because the moon's moving and the earth is moving and they're moving through space. So maybe the sun is a better frame of reference. The point is you can move your frame of reference for how you measure everything else to whatever you want. So like a car on the interstate moving 70 miles per hour east with respect to the ground, that's one way to describe that motion. But if you move the frame of reference from the earth to the car, then the car is now the thing that is stationary, and you measure everything else relative to the car. So I said a while ago that the car was going 70 miles per hour east, but now if the car is the frame of reference, then really it's the world moving 70 miles per hour west under the car, and everything outside the car is moving relative to the car. Okay, so let's look at some vocabulary. And we'll start with displacement. Displacement is just a change in position, and you need a frame of reference to tell if something's position has changed, because you measure where it is now relative to some origin, and then you measure where it is later relative to that same origin, and if it's not in the same spot, then you know it has moved. And we describe that movement, you can describe that change in position as displacement. Displacement is a vector because it involves direction, and it has a size. We will indicate displacement with, so first of all, position. Let's just say we're tracking the motion of something on a line, and let's call its coordinate x. So position can be written as x. Displacement can be written as change in x. So that symbol is an uppercase Greek letter. We're going to encounter quite a few Greek letters throughout physics and math. You might have seen this already in math when you were talking about slope, like delta y over delta x. Delta usually means, in the math or science context, it usually means change in some quantity, change in whatever you write after the delta. So here this means delta x, or change in x. IB physics also calls, more commonly, displacement s. So s is the same thing as delta x, and that is displacement. In the equations that we're going to learn that show up in the IB data booklet, which is really just the equation book, they will always call displacement s. But for this lesson, it's a little bit more instructive to call it delta x, because that really reinforces that it's change in position. So if this is 0, 1, 2, I'm just labeling a distance from this spot, which I'm going to call my origin, and I'll make the origin 0. If little Timmy is standing at the origin, this is little Timmy. Little Timmy's going to help us learn physics for these 2 years. So this is a big day. You've just met little Timmy. You should feel very honored. If he walks this way and stops right here, he has moved, and we know he's moved because his position was 0 and now it's 3 in this frame of reference with respect to this origin. So you could indicate that movement with a vector drawn from the beginning to the end and pointing in the direction that he went. That is a displacement vector. And it has direction. It points in the direction that he went. We can figure out its length. Its length you can find from change in position. So he finished at 3, and let's say these are meters. So 3 meters minus, he started at 0 meters. So his change in position is 3 meters. And by the way, when you calculate change in position, it's always going to be the final value minus the initial value. That f and that I, those are subscripts. That we will use a lot of subscripts in physics to label variables. So that means x final minus x initial. And change in anything is always the final value minus the initial value. So you could say final minus initial. That's really a good definition for change in some quantity. So his displacement is 3 meters, but what if you did not use the same frame of reference as me? What if in your frame of reference, this way was positive for you, and so that was, let's say, 7, 6, 5, 4, 3, ... He would have started here at 7, and he would have finished here at 4. So your delta x in your frame of reference would have been final, which is 4, minus initial, which is 7, which gives you -3. So what you'll see is that if I draw a vector for displacement from here, the beginning to the end, that red vector that I drew is the exact same red vector that I drew up here. There is no difference really between these two displacement vectors. The only difference is that I used a different frame of reference to measure the motion. And so the length of the vector, if I figure out the magnitude, magnitude of this vector, it's still 3, just like it was up here. The length is the same, and it's pointing in the same direction. It's just that in the blue frame of reference up here, the right was called positive. So you could say that vector is pointing in the positive x direction in this frame of reference. In the green frame of reference down here, the left is positive. So someone describing it in this frame of reference would say that that vector points in the negative x direction. But it is the same vector. The displacement is the same. So physics doesn't care about frame of reference. When you use equations of physics and when you describe quantities, they have meaning in all frames of reference. Yes, you have to be careful and decide on the directions in your frame of reference so that you can be careful, but you can always compare your answer to someone else's answer in a different frame of reference, and you should have the same answer once you understand how to translate from your frame of reference to their frame of reference. Okay, distance is the next thing that we need to talk about. And distance is very similar to displacement in some ways, and it's very different in other ways. They are not the same thing. So the easiest, I find, explanation for distance is to imagine a measuring wheel, which hopefully you've seen one of these before. It looks like this. That I like to call a distanceometer. That's not the real name for it. Distanceometer, like speedometer, distanceometer. That measures distance. It only ever measures distance, as long as you're rolling it forwards. So distance is a measure of total, let's say, ground covered, and that's not an official definition. It is not a vector, so it does not have a direction. It is always greater than 0. It just counts up. It doesn't decrease. You cannot decrease your distance traveled because it's always counting up. Like if you're rolling this thing forwards and you only ever roll it in the forwards direction, no matter which way you're pointing. I mean, you can go in circles. Like if you start here and follow some crazy path, but you're rolling this thing forwards the whole way, it will measure the distance that you traveled. However, since the start and the stop are the same point, what would the displacement be here? Yes, you guessed it. If the start and the stop is the same spot, then the displacement would be 0, but the distance would be some number greater than 0 depending on how far you went. So that's a big difference between distance and displacement. They are both measured in meters, and there are some situations where it might seem like distance and displacement are the same thing. Like if we look at this example up here, little Timmy went forwards and he stopped. So the distance that little Timmy traveled was 3 meters. And the size of his displacement vector is also 3 meters. So it seems like those are the same thing, but they're really different quantities. All right, now that we know about displacement and distance, we can talk about velocity and speed. And velocity and speed began to have meaning when Galileo invented a way to reliably measure time using pendulums. Before that, you couldn't really put a number to speed or velocity. People knew that things were faster than other things, but they had no way of quantifying it with numbers because there was no reliable way to time anything. But once the pendulum came along, there was a reliable way to time things, and you could actually get a number for time. And so quantifying how far something travels in a certain amount of time began to make sense. So velocity is officially an object's displacement divided by the time it took to do that displacement. So you could write it like this. Velocity is a vector. And a good tip for if a thing is a vector is if it is set equal to another vector. So displacement is a vector. And since velocity involves displacement, then velocity is a vector. Sometimes there are exceptions to that, but for now, that's pretty much true. If you divide displacement by the time it took to do that displacement, you get the size of a velocity vector. And the direction of the velocity vector is the same as the direction of the displacement vector. So in the example with little Timmy, if he went from 0 meters to 3 meters, and let's say that took someone had a clock going, okay? And at 0 meters, the clock said 7 seconds. And then when little Timmy was at 3 meters, the clock said 13 seconds. So what would you plug in for displacement and time in this formula? So displacement we already figured out on the last page was positive 3 meters in this frame of reference when it's increasing to the right. And time, it's change in time, so that's final value minus initial value. So 13 minus 7. So 13 minus 7. which is 6 seconds. So that's 3 divided by 6, or 0.5 meters per second in the positive direction. So when we were learning vectors, you needed to describe an angle, usually to tell me the direction of a vector. But since this motion is just along a line, the only thing little Timmy can do here is walk forwards or backwards. So really the only kinds of vectors that exist on this line are things that point to the right or things that point to the left. And we can indicate that with plus and minus. So vectors in one dimension are really easy. You just use pluses and minuses, and you don't ever actually have to use sine, cosine, or tangent or anything like that, because the vectors always line up. And if you have a vector that's lined up with another vector, you really can just add together their sizes, and that's the sum. Or if you have a vector that is pointing in the opposite direction of another vector, you really can just subtract their differences, and subtract their sizes, and that would be the difference between them. So one-dimensional vectors are really basically just positive and negative numbers. So if you want to indicate direction in one-dimensional motion, which is what this is, you can track Timmy on a line, you just need a plus or a minus sign. And one-dimensional motion is a little bit more useful than it might seem at first. Like a thing falling through the air, if it's falling straight down, that's one-dimensional motion, because you can put a line on its path and it follows that line. If the thing is rolling or sliding down a ramp, you can line up a line that follows the path of that object, therefore it is one-dimensional motion. Okay, speed is defined as, speed is not the same thing as velocity. Speed is the distance that an object travels divided by how long it takes. Some people say that speed is the magnitude of velocity, and that's not quite right. There are situations where that's true, but there are other situations where that's not true. So we're not going to say that. That's not quite right. It's a little more complicated than that. In simple situations, that might be true, but we can be beyond that for now. So you can't, IB physics really, you don't really need a symbol for speed because it doesn't come up that often, but you can't use S for speed to stand for speed because that is taken. Unfortunately, IB physics uses S to stand for displacement. I wish they used delta X exclusively like this. They don't. And it does make some equations shorter to just write an S, but why do they use an S? I think it's an old Latin word that stands for distance or displacement. And so this is, you see S often in non-American physics textbooks, but in American physics textbooks you usually don't see an S. And since IB is all international, we're going to stick to that. So eventually we will switch to just using S to stand for displacement, but I don't want you to try to use it for speed now or then, because things will get too confusing. So I'm just going to write out the word speed instead of coming up with a symbol for it. Speed is distance divided by time. Speed's always going to be greater than 0 because distance is always greater than 0. Speed does not have a direction. It's a scalar. The units of speed are meters per second. All right, an example to tie all this together is, let's say little Timmy, this is a normal track like in track and field, and little Timmy starts right here and he runs in this direction all the way around and he stops at the beginning of the straight section right here. I've been told by reliable sources that the distance of the straight section on the edge of a track is 100 meters, so we'll trust that. So the finishing point for little Timmy was here, 100 meters before where he started. So can you find displacement, distance, velocity, and speed? Do those things for class tomorrow. Good luck.